So here we want to find the derivative dy dx of the following function. And the derivative dy dx means that we want to find the derivative of y with respect to x. Now, if you take a look at the function that we have here, this is not a function that is explicitly defined, right? We don't have a function y equals some expression in terms of x. That could be x squared, it could be x squared plus x. It could be a multitude of different functions, but that's not what we have here, right? We don't have y equals some expression in terms of x. We have a function where x and y are found on the same side of the equation. We don't have one variable solved for the other. We have x and y mixed together, right? Our function is e to the power of x times y plus x squared minus y squared equals 10. This is what we would call an implicitly defined function. And so when you want to find the derivative dy dx of an implicitly defined function, you have two different options. You can try to solve for y first and then take the derivative with respect to x, or you can use the method of implicit differentiation. Now in this case, we are going to use implicit differentiation because solving for y or isolating y in this function would prove to be a little bit tricky. It's not something that would be worth our time to try, because not only do we have a y squared right here, but we also have y within the power of this exponential function. So we don't want to try to isolate y or solve for it. What we should do instead is use implicit differentiation by taking the derivative of both sides of the equation with respect to x, and remembering how to treat the variable y when we use implicit differentiation. And you'll see what I mean as we work through this derivative. So what we're going to do is take the derivative with respect to x, or d dx, of both sides of the equation. And so first up, we need to take the derivative with respect to x of e to the power of x times y. Now, what we have here is an expression that, in order to take the derivative of, is going to require the chain rule, right? We have a composite function right here, a function within another function. We have this function or expression of x times y within this exponential function of e raised to a power. So what we have to do is use the chain rule. We'll take the derivative of the outside function and then multiply by the derivative of the inside function. All right, now remember, the derivative d dx of e to the power of x is equal to e to the power of x. So the derivative of the outside function here is just going to be e to the power of x times y. But since that power is not just x, we will need to use a chain rule and multiply by the derivative of that inside function. All right, but one thing at a time here. Let's just start by writing this. We're going to have e to the power of x times y, and then we're going to multiply by the derivative of that power, or of that inside function. And this is where things get a little bit tricky, because we're taking the derivative with respect to x of x times y. Now, when you do implicit differentiation, like we are doing here, whenever you have a term that involves multiplying x by y, what you have to work with is the product rule. And if you don't remember the product rule, it looks like this. If you're taking the derivative with respect to x of one function, f of x, multiplied by another function, g of x, the derivative is the first function, f of x, multiplied by the derivative of the second function plus the second function, g of x, times the derivative of the first function. So that'd be f prime of x. Okay? Or you could reverse the order of those two terms if you like. Since we're adding them together, it doesn't matter what order you do those calculations in, but make sure to multiply the first function by the derivative of the second and add it to the second function multiplied by the derivative of the first. So in this case, our first function, or first expression, would be x, and our second one would be y. So we're going to have x times the derivative of y, and the derivative of y with respect to x is dy dx. So we're going to have x times dy dx. Then we're going to add that to the second function multiplied by the derivative of the first. So our second function is y, so we're going to have y times the derivative of x, and the derivative of just x is 1, right? The derivative of x to the first power is just going to be equal to its coefficient, which in this case would just be 1. And so that will complete our product rule, which also completes our chain rule, right? So let's review what we just did here. We took the derivative of the outside function, so it's just e to the power of x times y. You keep the same inside function when taking that derivative, and then we multiplied by the derivative of that inside function, x times y, which is this right here. Okay, now let's move on. We need to take the derivative of these two terms yet, as well as this side of the equation. The derivative of x squared, that's pretty simple. We just use the power rule for derivatives, multiply the exponent down, and subtract 1 from the exponent. So we'll have plus 2x. And then we need to take the derivative of negative y squared with respect to x. So the first part of that is we will treat it as if it was x. So we'll take the derivative of this as we would normally if it was negative x squared. So what I mean by that is the derivative will be negative 2y. Use the power rule for derivatives, multiply that 2 down, subtract 1 from the exponent, so you have minus 2y. But then because you're taking the derivative of y with respect to x, you also need to multiply by dy dx, okay? You can't forget that part of this process. And then that's pretty much it for that term. This will all be equal to the derivative of 10 with respect to x, and 10 is just a constant, and the derivative of all constants is 0. Okay, so now we have taken the derivative of both sides of this equation with respect to x, but now in order to actually find the derivative of that implicitly defined function, we need to solve for dy dx, right? That's what we want to find. And we have two dy dx's in this equation, so what we want to do here is try to isolate it, try to solve for dy dx by manipulating our equation in some way. And the first thing that I think we should do here is distribute e to the power of x times y through this quantity. That way we're just going to have a string of terms that we can then organize to our liking, and you'll see what I mean by that. Let's just multiply e to the power of x times y through this quantity. If we do that, we'll have x times e to the power of x times y times dy dx plus y times e to the power of x times y. All right, so I multiplied this by the first term, and I just move the x out front. Doesn't matter the order in which you multiply those things together. It's going to be the same regardless. So we have x times e to the power of x times y times dy dx, and then we multiplied it by this term, so we just have y times e to the power of x times y. All right, then I'm just going to rewrite the rest of our terms. We have plus 2x minus 2y times dy dx equals 0. Okay, so now our next step in this process to solve for dy dx should be to separate our terms. We want all of our terms in this equation that include dy dx to be on one side of the equation, and then we want everything else on the other side. So what that means for us is that these two terms right here, y times e to the power of x times y and 2x, we want to move those over to the other side of the equation by subtracting them from both sides, and that will just leave us with these two terms that include dy dx on the other side. And you'll see why that's important pretty soon. But let's do that. If we move these two terms over to the other side of the equation, they will become negative. So we're going to have x times e to the power of x times y times dy dx minus 2y times dy dx is equal to negative 2x minus y times e to the power of x times y. All right, so now these two terms are on this side of the equation, which means they are now both negative. Now, what that does for us is we now have just two terms on this side of the equation that both include dy dx as a common factor, so we can pull out that common factor, and then we'll be able to solve for dy dx. All right, so let me show you what I mean. Let's continue our work up here. If we pull out the common factor of dy dx out of both terms, we'll have dy dx times x times e to the power of x times y minus 2y, and that will be equal to negative 2x minus y times e to the power of x times y. All right, so I pulled dy dx out of these two terms, and so we're just left with x times e to the power of x times y right here, and then minus 2y right here. Okay, if you were to distribute dy dx back through this quantity, you would get those two terms once again. All right, so these two expressions are equivalent. Now, solving for dy dx is as simple as just dividing both sides by this quantity. If we divide both sides by that expression, or that quantity, all that will be left on this side of the equation is dy dx. We will have solved for it. So let's do that. If we divide both sides of the equation by x times e to the power of x times y minus 2y, we will have that dy dx is equal to negative 2x minus y times e to the power of x times y divided by x times e to the power of x times y minus 2y. And that's it. That right there is the derivative dy dx of this implicitly defined function. Okay, so just remember, when you want to take the derivative of an implicitly defined function, you always start by taking the derivative with respect to x of both sides of the equation. Remember that whenever you take the derivative of an expression with y, that you need to include that factor of dy dx, and after you do all that, you want to isolate dy dx by moving all the terms that do not have it to the other side of the equation. Then you pull out that common factor of dy dx, and then solve for it by dividing both sides by the quantity of the terms that you pulled that dy dx out of. Okay, if you have any questions, feel free to leave those in the comments. But if you don't have any questions, that is it for this example and this video. If you want to learn more about implicit differentiation and other Calculus 1 topics, I have a whole playlist of all of my Calculus 1 videos that you can check out, and so feel free to take a look at that. But with that, that is all I had for now, so I will see you next time.